So we're going to take a look at some word problems that cover the topic of growth and decay. But before we get into the word problems, let's look at the formula for growth and decay. And let's look at what does each represent. When I say each, the formula, y of t is equal to a times e to the kt power. What does y of t represent? What does a represent? What does k and what does t represent? So I want us to take a look at that. So y of t, this represents the value at time t. Then we have our a. Well, our variable a in this formula here, which is the value at the start. We have t, which represents, of course, the time. And then we have the variable k, where k represents either the growth or decay. But when k is greater than 0, it's the rate of growth. And when k is less than 0, it's the rate of decay. So this is a standard formula for growth and decay, but depending on the word problem and how it's set up, it will be, we may use different variables, but it's going to be situated in a way that where we have a value at the start given, we may be given the growth and decay, and we are also given the time, and then we may be asked to find the value at that time t. So let's take a look at the first question, where we have here, it says the size p of a certain insect population at time t in days obeys the function. We have p of t is equal to 500 times e to the 0.05 t. So we're going to use this formula. Now this is the formula that represents um, actually growth, okay, because our k in the formula is 0.05. So let me write out the formula so that you can see this a little bit better on the screen. Times e to the 0.05 t, and 500 represents the value at the start. 0.05 represents, since this is our k and is greater than 0, the rate of growth. So we have several parts in this particular word problem that you'll be asked certain questions. So let's look at part A. It says determine the number of insects at t equals to 0 days. Okay, so t equals to 0 days. So we want to find the number of insects. So starting at 0, so we have p of t. We're going to substitute 0 in for t times e to the 0.05 times 0. That would give us 500 times e to the 0 power. And we know that e to the 0 power is 1. So if you need to use your calculator to find out what is the value, but that's one of the properties we've covered. So we want to find e to the 0 power. That gives us the value of 1. So we have 500 times 1, which is 500 insects. Okay, so at the first day, we have 500 insects. Okay. For B, it says, what is the growth rate of the insect population? And in my math lab, it's going to ask you to write your answer as a percent. So we already identified the growth rate. This is our K. So our growth rate, just by looking at the formula, is 0.05, 0.05. But we're going to write this out as a percentage, and that will give us 5%. All right, next, letter C. It says, what is the population after 10 days? So we're going to let T represent the 10 days. We're going to plug 10 in for T into the formula to find out how many insects that we have after 10 days. So we have P of 10 is equal to 500 times e to the 0.05 times 10. We have 500 times e to the 0.5. And then we're going to enter this information into our calculator. So I'm going to first put in e to the 0.5 first, and then press enter, and then times that by or 500. And we have 824.36066354. But in my math lab, it's going to ask you to round to the nearest whole number. Okay, so round to the nearest whole number, and that will be 824 insects. All right, let's do part D. And if you have any questions, just make a note to ask me in class when I see you next class day. All right, example D. It says, when will the insect population reach 600? All right, so we want to find out at what day will the insect population reach 600. So what is given here is P of T, value at the time. So don't forget about our formula. P of T is equal to 500 times e to the 0.05t. So we're going to plug 600 in for P of T, and we want to find the time, the day, or days. So we have 600 is equal to 500 times e to the 0.05t. We want our base e to be by itself, so we're going to divide 500 to both sides. And 600 divided by 500 gives us 1.2 equals to e raised to the 0.05t. So to solve for t, we want to take the natural log to both sides. And remember, the natural log e raised to a power is going to equal to that power. So on the right hand side, we have 0.05t. Left hand side is ln of 1.2. Solving for t, we're going to divide by 0.05 to both sides. And we have t is equal to, let's go ahead and enter that information here, ln of 1.2 divided by 0.05, and we have 3.6464311136. In my math lab, it's going to ask you to round to the nearest tenth. So let's take this decimal answer and round it to the nearest tenth. And we have 3.7. Okay, so when will the insect population reach 600? 3.7 days. Okay, and the last example, E, when will the insect population double? Okay, so we already know that in our formula, P of T equals to 500 e to the 0.05t. The 500 is our initial population, insect population. So it wants to know when will it double. So we want to um, let P of T equals to 1,000. Okay, so this is our example E. So let's plug 1,000 in for P of T. So we have 1,000 equals to 500 times e to the 0.05t. We want our base e to be by itself, so we're going to divide 500 to both sides. And we have 2 is equal to e to the 0.05t. To solve for t, we're going to take the natural log to both sides. And we know the right-hand side is going to equal to 0.05t. And we have ln of 2. So solving for t, we're going to divide by 0.05 to both sides. And we have t is equal to, so let's enter this into our calculator. ln of 2 divided by 0.05, and we have 13.86294,361, and we're going to round to the nearest tenth for our answer, and this rounds to 13.9. So when will it reach, the population reach 1,000? That would be 13.9 days. There we go.